Welcome, everyone. Today, we're going to do a bit of a masterclass on a problem that trips up countless developers, migrating complex applications from x86 to Arm. We're going to break down, step by step, how to automate what is usually a very, very painful manual process.
Okay, so what's the plan? First up, we're going to smash into what I call the migration wall to really understand why these projects fail. Then we'll design the automation engine that's going to help us break right through it. After that, we'll see the engine in action. And finally, we'll look at the incredible time-saving payoff.
All right, let's head over to the whiteboard because I want to sketch out a scenario that, well, if you're a developer or a DevOps engineer, you've probably lived this nightmare.
So, you've got your containerized app, right? Moving it to Arm. What could possibly go wrong? It seems so simple on the surface. Just change the target architecture and hit rebuild. But as we're about to see, there are some nasty little surprises hiding in there that can stop a migration dead in its tracks.
Okay, so picture this. On our whiteboard, I'm drawing a box. And this is our starting point, a legacy application. It's built for x86, it's running on an ancient Linux distro like CentOS 6, and deep down in the code, you've got this hand-optimized C++ using something called AVX2 intrinsics.
And the goal? Oh, the goal is beautiful. We want to get this thing running on a modern ARM-based cloud instance, like an AWS Graviton chip. Why? Because we want to save a ton of money and get way better performance. But when you actually try to do the simple thing, just rebuild it and run it, you get this. I'm literally drawing a giant red X right through our diagram. Migration failed. The question is, why? And here's the thing. This isn't just one bug. The failure is happening at every single layer of the stack. I mean, the Docker base image for CentOS 6, it doesn't even exist for ARM. The compiler flags are hard-coded for x86. The C++ source code itself is calling Intel-specific functions. And get this, even the core logic, how it processes vectors, is just completely incompatible. And this right here, this gets to the very first roadblock, your build environment. The Docker file itself is basically an x86-only document. You can't just run it. You have to totally rewrite it, from the operating system it's based on, all the way down to the tiny little flags you pass to the compiler. Okay, and now for the really tricky part, the source code itself. Look, this isn't a simple find and replace job. We're talking about super low-level, performance-critical instructions. Trying to translate these by hand? It's just incredibly tedious, you're bound to make mistakes, and honestly, you need to be an expert in two totally different CPU architectures to even attempt it. Okay, so we've painted a pretty bleak picture, right? Doing this manually is just a massive headache. So that pretty much makes the case for us. We need an automated solution. The question is, how do you build a machine that can actually do all of this for us? The heart of this automation engine is this thing called the Model Context Protocol, or MCP. The absolute best way to think about it is like a universal adapter for your AI assistant. It basically gives a tool like GitHub Copilot superpowers, letting it securely connect to, and here's the key part, run other specialized containerized tools. So back to our whiteboard diagram. The Docker MCP Toolkit sits right in the middle. It's the conductor of this whole orchestra, It's managing all these powerful tools, making sure they run safely and do what they're told. For this specific job, we plug 3 key servers into our hub. First, the Arm server. That's our expert. It has all the migration tools. Then the GitHub server. It knows how to talk to our code repository, create pull requests and all that. And finally, the sequential thinking server, which is kind of like the project manager. It helps the AI break down this big, messy problem into a clean, logical series of steps. So let's draw the arrows on our diagram. As the developer, you don't go anywhere. You stay right inside VS Code and just talk to GitHub Copilot. Copilot then talks to the MCP gateway, and that gateway becomes the puppet master, orchestrating all these powerful tools in the background to get the job done for you.
All right, theory's over, now for the fun part. Let's actually watch this engine in action and see it automate the entire migration of that broken app we started with.
The whole thing happens in this beautiful, logical 4-step flow. It's basically doing exactly what a human developer would do, but instead of taking hours or days, it executes in minutes. It analyzes the code, converts the stuff that won't work, transforms the entire build environment, and then delivers a completely finished product.
And check this out. It all starts with a single, detailed prompt to GitHub Copilot. You're not just asking a simple question here, you're giving a command. You're telling it the goal, and you're pointing it to the specialized tools it now has access to thanks to MCP.
This slide really shows the magic of that first step, the analysis. If you were doing this manually, you'd be digging through files for hours, just searching for weird flags and function names. But the automated scan tool, it just instantly pinpoints every single architecture-dependent line of code and spits out a perfect report in seconds. All the guesswork is just gone. And what's the grand finale? It's this, a perfect, automatically generated GitHub pull request. It's totally ready for a human to review, and inside, you've got the modernized Dockerfile and the completely refactored C++ code. Done.
Okay, so we've seen the how. Now for the most important part of this whole story. What's the payoff? What does all this slick automation actually get us? Let's break down the numbers. I mean, this comparison table says it all, doesn't it? And it's not just about saving time, even though it saves a lot of time. The manual way is just full of hours of boring research, frustrating rewrites, and chasing down compiler errors. The automated flow just vaporizes all of that. It completely changes the developer's job from being a tedious code porter to a high-level strategic reviewer.
Okay, let's put a real number on this. For an app like the one in our example, a senior developer would probably spend somewhere between 5 to 7 hours of solid, focused work to get this done manually.
And with the Docker MCP Toolkit, that entire process, from writing the prompt to getting the final PR, is crushed down to about 25 minutes. Let's circle that number big and bold on our whiteboard. That's the game changer.
So let's wrap this up with the big idea here. This isn't just about rebuilding a container image. That's easy. This tech proves we can automate the really hard stuff, the deep, complex, error-prone code transformations. And that should leave you with a really exciting question. What's the next complex, painful workflow in your job that you could automate away?